In calculus of one variable, you have the idea of tangent line to a function. So this is if you've got some curve, we take a point, we have the line that well approximates the curve, and the tangent line has the slope given by the derivative at a given point. So we have this tangent line approximation to a curve. With functions of more than one variable, we no longer have a tangent line. Now we have the notion of tangent plane. So a tangent plane is playing the same role. We've got some 3D surface, imagine some cap like this, and then at this point we've got this surface heading out in each direction, this plane, and the plane now must be somehow given by maybe the derivatives of the curve. And the way we can see this is we're going to use a property of the gradient, where the gradient of f is perpendicular to level sets, level curves of f. So the gradient of f is perpendicular to level curves, and we can use the idea then that if it's perpendicular, that means it'll give us a normal vector, and the normal vector we can use to get the equation of the plane. So we're going to use this property right here. Let's maybe look at an example. Say we've got the sphere x squared plus y squared plus z squared equals 9, and we want to find the equation of the tangent plane at the point, say 1, 2, square root of 5. Let's try that again. 1, 2, 2. Right, we square this, we get 1 plus 4 plus 4 is 9. So at the point 1, 2, 2. So what we'll do first is we'll take the gradient. First we want to rewrite this so it looks like a level curve. So we're going to rewrite this as x squared plus y squared plus z squared minus 9 equals 0. Now this part right here is playing the role of the f. So we take the gradient of f, the gradient of x squared plus y squared plus z squared minus 9. We'll go through and take our vector of partial derivatives. So the partial with respect to x is 2x, the partial with respect to y is 2y, the partial with respect to z is 2z. But now we want to evaluate this at the point 1, 2, 2. So we plug 1 in for all the x's, and we get 2. We plug 2 in for the y's, we get 4. We plug in 2 for the z's, and we get 4. So this is our normal vector. It's the vector that's perpendicular to this level set, this level surface. So we have the normal vector, and we have a point. So now we can use the standard form for a plane, which is the normal vector dotted with x minus our starting point. So this is 2 times x minus 1. Right, the 2 came from our normal vector, plus 4 times y minus 2. The 4 came from the normal vector and the 2 came from our point, plus 4 times z minus 2 equals 0. Then of course you can simplify this. You can divide everything by 2 and then maybe get everything to the same side, but that's the gist of how you find a tangent plane at a given point. Now it's worth noting that if we have a surface that isn't given by a level set, so let's say for example we want to find the tangent plane to z equals x squared minus y squared at say the point 2, 1, 3. Well, first it looks like this z is a function of x and y. We're not taking the gradient of the right hand side. We want to rewrite this so it looks like the level set of a function of 3 variables, not 2 variables. So we always want to rearrange this so we have a 0 on one side. So we move the z over, and this looks like x squared minus y squared minus z equals 0, and now we go through the usual take the gradient, plug in the point, and so on. So I just want to point out that this right here is not the f that we're using in this formulation of the normal vector. We actually want to move the z over and treat this as f. We've got to have a 0 on the or at least a constant on the other side of the equation. So now we have the idea of tangent plane, there's also the notion of normal line. So the normal line really isn't anything more complicated. So the equation of the normal line, well, first we need a direction vector. Anytime we have a line, we need a direction vector. And the direction vector is going to be the normal vector that we found in the previous step, because it's the normal line is perpendicular to the surface, so its direction vector is perpendicular to the surface, and that means it's a normal vector. So the direction vector of the line is the normal vector. So if we wanted to take the example we did previously, where we had x squared plus y squared plus z squared equals 9, and this was at the point 1, 2, 2. So our normal line, well, first we found that the normal vector was 2, 4, 4. This is what we had done in the previous example. So now this is the direction vector for this line. And remember, a line r of t is given by, well, we take the direction vector, in this case the normal vector, so 2t plus our starting point, and then the y is 4t plus the starting y value, and then we've got 4t plus the starting z value. So this is the equation of the normal line given to that same surface. So these are the two generalizations we have of tangent line to a function of more than one variable.